Good afternoon, student from the course TEQU 4006. Today we're going to discuss a little bit the Runge Kutta numerical method. Some people pronounce Runge Kutta, others pronounce Runge Kutta, and others pronounce Runge Kutta. The Runge Kutta that we're going to be talking, there's different order. We're going to be talking about the fourth order, which we're going to be using for first order ordinary differential equation. As you can see, this fourth order will calculate for slope, so it's a lot better than the Euler version. A little bit harder to implement, but a lot better. Remember, the Euler version only calculates one slope. Basically, if you remember, that would be like a K1 here, this slope here. But in the case of Runge Kutta of fourth order, we will calculate basically four slope, which going to be K1, K2, K3, as shown here, and finally a K4. With those four slope, then you will predict a better value of what the dependent variable will reach. And that's done within the step that you are studying, in this case called H, that H step. So again, Runge Kutta will calculate four slopes, and based on that, it will try to estimate a better value for the dependent variable, whatever it is in this case. Now, let's continue with that. So let's put an example here, a very simple example. A falling object under air resistance, like a baseball, as shown here. And as you can see, this ball is falling, right? And it's falling based on a force that is called mg. That's the mass of the ball times the acceleration of the earth. That would be the force downward. And now there's some forces that will kind of resist falling of the ball, and that will be the buoyancy force and resistance or the drag of the air as the ball falls down. Now we're going to take positives going down to the earth, and the idea will be like this. You start with the Newton's law, that the net force equals mass times acceleration, and then from the concept that acceleration is nothing else than the change in velocity versus time, here you get basically your differential equation as the ball falls. Now, if you separate and put in terms of the change in velocity versus time like this, you end up with this equation. Now, the only thing that we need now is to add those terms required for the change in velocity with respect to time. And that's basically that net force will be the force downward, that's mg, minus the drag force, which is going in the other direction. And that will be 1/2 rho times the coefficient of drag times the frontal area of the ball times the speed or the velocity to the square. So as you can see, all this divided by m. Now I delete the buoyancy force because it's pretty much negligible compared with the density of the ball. So this will cancel out less than 1% in most cases. So I would not consider this. You can add it if you want to, but I would not consider this at this time. So my differential equation will end up looking more like this. All right. Now a little bit more of simplification of that. This is the equation. If you see, I divide by m. The m cancel out here, but it end up here. So all these terms here are constant, basically. Now, I would say that they are constant. The coefficient of drag, somehow, it is a function of the velocity. Basically, the Reynolds number. I would not complicate this problem with that, but you could definitely add that the CD, the coefficient of drag, it is a function of velocity as well, and will make this equation even more non-linear than what it is right now. If CD is a function of velocity, then you will end up having here a very complicated equation to try to solve analytically. But by leaving the equation the way it is right now, saying that the coefficient of drag is a constant, it is a number, and everything else is a number that will not change either with time or with velocity, then I can take all these parameters and put it in a constant beta. So my differential equation end up like this. Very simple. Now, the initial condition for this problem is that at time equals 0, you drop the ball from whatever elevation that you are located. It's dropping the ball. You don't add any velocity to the ball. You just let it go. And with that in mind, we can then use, as you can see here, since g is not a function of time, it's a constant, we can take all these or all these here and do variable separation. Okay? And as you can see, we end up with this equation equal to the integral of this part here, the right hand side, which is equal to t. Not a big deal. Now, to integrate these, you can use partial fraction, recognizing that this is, we can apply differences of square, so they end up looking more like this, right? And this comes from an integral table, number 14. I forgot to put the reference. I will put it right at the description later on. So when you compare what you have here, eventually you end up with an analytical solution looking like this. I might add all the steps required to get to arrive here, but in the meantime, this is it. This is just the analytical solution for a problem like this. All right. Now, eventually, you know, it's very interesting to notice that as time goes to infinity, these two terms will cancel out, equal 1, the division of this over this, and you end up with only this. And this is called terminal velocity. So eventually, the ball will reach a particular velocity, which is termed terminal velocity at, you know, when time goes to infinity, which is not something like it's a lot of time. There's not a lot of time. Within few seconds, the ball will reach that particular velocity. Interesting, right? So the next slide is now the application of the method. Let's see where we are. Here we are. This is how we apply the fourth order Runge Kutta method. This is come from the Numerical Method for Engineering 7th edition by Stephen Chapra and Raymond Cannell. This is a copy of what they have there for the fourth order. You have happened to have a differential equation looking like this, and the arguments are x and y, which are basically x is the independent variable and y the dependent variable. Then you have the solution for that differential equation. The next, the future value based on the present value will be as shown here. 1/6 of the sum of the slopes multiplied by the step that you're using. Now, each of these slope need to be evaluated at a given argument. And here's the argument, xi, yi, which are basically the values that you know from the beginning at time equals 0. And k2 basically is the same value that you know from the beginning, but modified by this argument here that, as you can see, this is 1/2 of the step, and the y by 1/2 k1 is being used time h, and so k3 and so k4. So you happen to have both arguments as required to calculate those slopes. Now, in our particular case, it's straightforward because we only have one argument. From here, we only worry about the y argument here, only this part here, because the independent variable, time, is not here. Since time is not here, that makes the application of Runge Kutta method a lot easier. All right. So again, remember, only one variable here, and that's the dependent variable. So we only need to worry the argument here. It's like instead of having f of I, comma, y of I, this equal f of y sus I only. That's the only thing that you need to worry about. And so this part here, so this part here, this part here, you don't need at all the independent variable argument because it's not in this equation. Make life a lot easier. In terms of our application, I mean, it is the computer that will do all the calculation for you. So again, the definition of beta, there's a definition for that. And so how we solve all these, our differential equation using the Runge Kutta method? Very simple in Excel. We go to Excel. I'm only showing here. I will go back to Excel and do the live demonstration of all this. But in the meantime, just so you understand what we are doing. Basically, you have to define all your variables, like for example, what is going to be beta. So you have to define what is rho with the proper unit. That's the density of the air. G, the acceleration, 9.81 meters per second square. The coefficient of drag, again, this is, I put this as a constant of 0.5. It depends of the Reynolds number. It might drop 2.3 or so forth, depending on the velocity of the ball. But again, for the sake of the argument, I just leave it as a constant for now on. Ball diameter is about 74, 75 millimeters, but in meter is what we got here. What else? Ball frontal area. You take this diameter, square them up, multiply by pi, divide by 4. You get the ball frontal area, the one that will be, resisting the air. The ball mass is about 145 grams or 145 kilograms. What else we got? Now, when you put all those parameters as shown here, that will give you the beta value. Now here I also calculate the terminal velocity, because basically I need it eventually for when I want to calculate the velocity, the analytical solution. So it's right there as well. And this term here, beta times g, well, that's the argument that is shown here. Beta times g, the square root of that is right here. So I calculate that as well. Now delta t, I put like 0.1, but this has some, there's some thought behind why I put 0.1, and it has to do with this equation. Like for example, if I want a delta v that change the velocity every, like a delta v of 1 at least, or close to 1, what would be a proper value of delta t? Basically, you put this equation on terms of delta t, and you end up with delta v over all these. At time 0, this term is 0, so you end up with delta v over g. Now, if delta v is 1 and g is 10, for the, just to make the math easy, you will see that delta t is 0.1, and this is where this comes from. So that's the precision that I need on the time to allow the speed or the velocity to change, basically on a 1-by-1 basis and so forth. All right. So now that I have delta t, it's very straightforward to put all this equation as shown here. Like for example, let's start easy on this one. As you can see, I have the time here. I have the Runge Kutta velocity calculation, which is basically this equation here. But to use this equation, at least from here and on, from this row and on, you are using this equation, but you need all the slope calculation. So the slope are here, K1, K2, K3, and K4. How about the arguments that are inside? Remember, for K1, I only need the initial velocity, which is 0. So that's what you see here, the 9.81, because you put v equals 0, so that the first slope is basically g, and g is 9.81. Now, to get K2, you need a different argument, and the argument is 1/2 the value of K1 multiplied by the step that you are taking. So all that is shown here end up being this number. This number is important because I'm going to be using this number to calculate now my new value of K2. So K2 is evaluated when I'm using this argument as shown here. The same is for K3. The K3 argument is basically the initial value, which is 0, plus 1/2, I'm here in K3, 1/2 times K2, whatever I got on this value here, multiply here, but also by the definition of the delta t. And that will provide me the argument that I need for K3. And here is K3. So you take this here. So you substitute g minus beta times v squared, which is this value is the v squared. All right. So I got K3. Now for the last one, K4, basically you again use the initial value, which in this case is 0, plus K3, whatever you get, whatever value you got here, time the step, and finally you get this argument, and that's the one that you use here again. So that end up with your forced slope. Now that you have the forced slope, then you apply this formula, but when? Here. So this result here is equal to the previous result, which is 0, plus 1/6. Now here you have K1, which is come from the line above, K1, K2, but K2 needs to be multiplied by 2, K3 as well needs to be multiplied by 2, plus K4. And here is the K4, and all that multiplied by 0.1. And that hit you with the 0.981. All right, when you have this value, then you have to modify again your K1, your K2, your K3, and your K4, and the arguments as well. They are modified as you have a new value of the velocity of the ball falling down. Now, is when you have this first, actually, when you have this first line already written, you can copy, that line up down here, and that will produce the next value that you need for this one here. So when you have all these lines now ready, if you keep, dragging, actually is the word, when you keep dragging this result down, then you will have the other results until the velocity of the ball get into what is called terminal velocity. What is interesting that at the same time I'm plotting, or actually calculating, what is the analytical value at also the given time shown here. And I'm using this equation is the one that is here on this column on the analytical solution. Again, and this velocity is in the unit of meter per second. All right. Now, let's go live with my Excel, and let's finish this because we are pretty much done. Here in Excel, and basically, let's see what we could do. You can go inside. These two values are the initial value at time 0. As I said, you are dropping the ball, so the initial velocity is 0. The analytical solution is the whole formula. So when time is 0, then the velocity is 0. Now here, you can start to see the arguments, and in this case, K1 don't need any argument except to take this value, and let me hit it again. You see, take this value and do the math. That will be G minus whatever is this value here, which is beta, time this velocity, but that velocity as following this formula here is to the square. So that's basically it. It's a little bit more complicated when you get here, because now this is the argument. I'm using this to understand what I need to put here. Double click. So that argument will be this velocity times one half, which is this 1/2, time K1, but K1 is coming from the D14, time $11. $11 is the value of H, or the step, and that's it. When you have that, then you substitute this value in order to calculate K2, then you are using that value as the velocity that you need to put on the equation, which will be G, again, $3 minus beta, that's $A, times the velocity, which in this case is this velocity elevated to the square. And that will do. So that's basically how this will go on each one. What would be nice now is if I plot, which basically is just not a big deal. If you see here, in each number is perfect. I mean, this the result from the Runge Kutta numerical method versus the analytical solution are just perfect. Now, let's increase the delta t to something that will start to make to make a difference between both methods. Let's say time of 1. Of time of 1, basically I see the first I mean, here is pretty much perfect. Even at a 1 second delta t, 27, 29. You see, there's a big, small difference basically at the second decimal place, but both arrive eventually within 11 or 15 seconds. We are already at the we call terminal velocity for this ball, falling down 32 meters per second. So we see we take a look at it, there's now, I mean, pretty much very close, the Runge Kutta model versus the analytical method. Now let's increase this to 2, or actually 3. I'm increasing it. So now you can see at 3 seconds. Yeah, it's kind of a different. Now we see a difference at the analytical, at the first decimal place here. No, say some start to kind of a Runge Kutta model start to fail a little bit at that level of 3 seconds, and so when the Runge Kutta fail, let's do that. Let's put a time a lot bigger than this. Let's say 5 seconds. Well, 5 seconds definitely way too much for Runge Kutta. It definitely failed, miserable. At 5 seconds delta t, pretty much it would not provide the right answers, as you can see here. So let's say 4 maybe. Yeah, 4, I said there's a difference, but it get the value done. 3 definitely will work okay. Yeah, with a value of 3, yeah, it hit pretty much. But the best, as shown, is 0.1. 0.1 definitely. Again, that comes from the fact that I want to see the change in velocity on a 1-by-1 basis. That's a delta v, proper delta v value. That will hit then a delta t of around 0.1, and both curves will overlap. There's no difference between both of the curves. Well, folks, that's basically it. There's nothing more into this. That's how Runge Kutta is set. All right. One thing that you might in the future trying to do is as you can see, this might be kind of a I would say this is a long path to resolve this problem. Runge Kutta, you might use, like, for example, going to developer and add like, for example, an equation using macros. You could do that, or Visual Basic, and so you could certainly do that and add your equation there, and then you will treat that equation like the same that is here, the same way that is shown here. So you don't need all these columns as shown here, because basically you will write them within the argument that are required for your function. So you write a function within Excel, this will be a lot easier perhaps to implement. Good enough up to here. That's it. Nothing more to add. Thank you. Have a nice day, and thank you for watching. Bye. All right. So now you are really interested in trying to get how you can get the analytical solution of this integral as shown here. So as I told you, we will try to use differences of square to get these into this form. This integral 14 here, the integral 14 comes from an integral table, and if I go back there in 1 second, let's see, there we go. Integral, that's this one. This one is the one that I'm using from this reference here, integral-table.com. You can get that from there, and I'm using 14. All right. So if I go back to here and open a little bit more space, we are here. So we want to integrate that. So we want to make this to look more like this. So let's do that very quickly. Like, for example, the first thing is that I see the x in this side as a positive term, but here is a negative term. So what I will do is divide the whole thing divided by beta. And if you do that, then you end up like this. Now, you don't like the negative there, then you multiply by minus 1, and you have 1 over beta, and this looks like this. So now we are ready to apply differences of square. We make life easier, and will look more like this. The chain and velocity equal v plus the square root of g over beta, parentheses velocity minus the square root of g over beta. So we have the positive term and the negative term. So when we compare this integral here, I mean, you can use definitely a partial fraction just to solve this problem, but I'm using the table. So when you compare these to these, then you know that the term a is equal to the square root of g over beta, and beta is just the negative of that same value. When you substitute these in here in the solution, so you end up, remember there's a negative 1 over beta here, but there's a negative here minus, so remember this is b minus a, but b is negative minus a, that's will make this negative as well, so minus minus, that's 2, they're identical, so you add them up together, and that's where you get the 2 here. But negative will end up canceling this negative as well, so you end up with this, what you have here. Remember, this is a, and this is, now why change here? Because b is negative, so you end up like velocity minus this term here, right? Now, this has to be evaluated between 0, that at time 0, you remember that time 0, the velocity of the ball is 0. You are dropping the ball to a given v value. So if you keep integrating this, I'm just showing you the result here. So that's all this times the logarithm of this part here between 0 and b. Any change that I did here? Let's see. Any more changes? Well, I did this b, beta, sorry, I incorporated inside, so that will be beta square, right? Just so that this end up looking good. Beta square over beta, that's cancel out one of the beta and end up like this. 1/2 square root of beta g times the logarithm of all these. So I clean them up a little bit. Next step is to apply the limit. At v for velocity, I end up getting this as a factor, and we have logarithm of all of basically the same, because we are evaluating at the velocity, minus, watch out for here. This is the part that sometimes confuses students. Minus the logarithm when v here is 0. Look how weird this get here inside. You end up with this term over this term, but this term end up being negative. And you've been told, you know, many years ago, that taking the logarithm of a negative value, that is trouble. That cannot be done. I understand that part. So bear with me. And this is why I'm trying to explain this, you know, so that you folks, you know, slow down, hold your horses. This is what's going to happen. So you end up with this minus a logarithm of minus 1, because this term is the same as this term except for this negative here. So you end up something looking very ugly. Minus the logarithm of minus 1. Now, if this were the case, only if you have to calculate this, that would be trouble. But that's not what we are doing. We have 2 logarithms here. How about if we take this logarithm and combine with this one? And that will make life easier, because you have the same term here coming back, but the logarithm here is the top part is okay, but this is minus, meaning that when you apply the logarithm rule, whatever is here will go to the denominator, and that's what I did here, minus 1. You see, that minus 1 will go here. Excellent, because what's happened next is you have t equal all this argument here times the logarithm of the numerator staying the same, but when you apply that minus 1 here, you end up moving this go positive and the v goes negative, and you end up with this term here. Excellent. So this first part here is t as a function of the velocity. And one thing that can happen from there is, as you might know, is that you don't want this term here to go negative, definitely. So when you compare that term equal to 0, so the maximum speed, which is called terminal velocity, is this term, g over beta, the square root of that. And that's the terminal velocity, and you are happy. Excellent, no big deal there. Now, and beta has this definition. The part that you saw in the table, it was not this way. It was written more like this. V is equal a function of time. So V as for velocity, right? Now, we need to change this equation, and let's see what we got here. And to do that, basically you multiply by this term, the denominator here, and when you do that, you end up having this simple equation here. If you take like, for example, elevate that to the e, to the exponent, so the logarithm will go away here, and you end up like this. But this term will have to be elevated to the e power as well. So instead of me writing all this many times, because basically I want to have this equation in terms of the velocity, I just equal alpha for the time being. If you do that, make life easier for the next calculation, and you end up having this term in the top equal alpha times whatever was in the denominator as shown here. So what you need to do is take the term, like for example, this term here will come this way, and this term here will go that way. So you end up with this expression here, and then you take the velocity as your common factor, 1 plus alpha equal this term here, and you put together some of the arguments, and g over beta will come out as a common factor. That would be alpha minus 1 divided by 1 over alpha. You recover back what was alpha, and you end up with this equation. That is the one that is the analytical solution. I hope you understand this problem. It's kind of fun, and see how well it gets you the solution. Remember this, there's some or assumption done just to get here, and one of them is that the coefficient of drag, which is in beta, is a constant value, and that may not be the case, and so forth. Oh well, that's it. Have fun, guys, and thank you for watching. Bye.